Hey guys, it's been a little while. We're going to continue on with our descriptive tutorial of how to do an animatronic eyeball. Basically, take any input device, record the movements, and play them back. In part one, we went over the electronics and how to assemble those. In part two, we went over the mechanical inputs and how those work. In this third part, it's going to be a little shorter. I'll explain in a minute. We're going to go over the eyeball mechanism, how the general mechanism works. Mechanism positioning, meaning how do you position servos properly to other devices so that they move properly, and a quick little tip on alignment. When you have mechanical devices that have to operate near each other and be in tight tolerance, how do we control that so we know it's positioned well? A minute ago I just mentioned that it's going to be a little shorter. There's a reason for that. My wife and I are closing on a new house, and you wouldn't believe how many documents you have to sign in order to prove that you're an honest person. So I spent the last week and a half finding forms, finding old papers, finding every little thing that they could want. So my time is pretty much taken up trying to get this house closed on. So time is short. So I'm going to try to do a little bit this week, but you may have to wait a little bit for the final part, which will cover the Arduino code and the basic structure and how that works and what the Arduino code is doing. And if I show you the basics of how that works, you can pretty much run with it and design your own robot if you want to. So with that said, let's get down to it. Eyeballs need to be able to move up and down and left and right and both at the same time. So up and to the right or up and to the left, which makes for an interesting joint. And in order to do that, we need to use what they call a U-joint or a universal joint. There are three main pieces. The center block, okay, two forks here, so those, and the third piece, which I use metal for, but you can use filament. So this is going to be our pin. Okay, so you got center block, forks, and pins. So let's put this universal joint together and talk about it. So I've already pre-drilled the holes a little bit, so I got 2.85 millimeter filament here. So what we're going to do is take our center block and one of our forks and pop the two together. And you'll notice you got a hole here that we can put the filament through. So we'll do that. And I'm going to trim the end off here. Flush cutters. And we'll do the same for the other side. Okay, there's one side, so now we got to pivot this way. Okay. Now we're going to take the other fork, put it on universal joint, and do the exact same thing. We're going to pin those. Okay, so we can fit it in the hole. Here we go. And we'll flush cut that. And we'll do the same to the other side. And there you go. And what's cool about the universal joint is since the pins are in line with each other, you have movement this way and you have movement this way. So we look at for the front, I can move up and to the right, up to the left, all around. So the universal joint is very important when doing animatronic eyes. And just a little fun fact, you can make one of these print in place. I printed this straight up and down with support material. And you can make your own universal joint. The downside here is obviously you got to have enough clearance in here so that they don't weld each other together, so you have a little more slop. But you can make your own universal joint as one piece. Again, as I mentioned before, in my mechanism I used ABS for the forks and the center block, and the pins were actually steel that I got from Lowe's, and trimmed them down, put them in there just so it was a little more robust, and I went and glued those in. So, but the same concept. One important thing when designing this, you may be asking, how do you know how long to make the fork to the pin and vice versa? Well, if you look at this eyeball here, which I designed off the average diameter of a human eye, it's a little bit, it's not quite half an eye, it's a little bit past. The center of rotation of a sphere is dead center, obviously. So what you want is you want the pins to be at the center of rotation for the eyeball, up, down, and left, right. Okay? So if we look at when I install this, here we go, the pins, see them back there, are pretty much at the center of the eye. So when I rotate left, right, and up, down, okay, they rotate around the center of the sphere. What you don't want is you don't want the pins to be, say, back here, because now your eyeball is going to swing and not rotate around its center. Same with going too far in, it won't rotate around its center. And if you rotate around its center, you can put an eyelid on it and everything can be centered around the pivot point. So make sure that your pins line up with the center of the sphere. So here's the eyeball mechanism, and let's look at the eyelids here. So remember when I said that the eyeball U-joint has to go through the center of rotation of the eyeball itself. That's important because the center of rotation of the eyelid here, the center of that has to go through the center axis of the rotation of the eyeball. So let's see if I can make this, that's gonna go left, right. So let's see if I can go up, down. There we go. So you get your up, down motion around, pivoting around that point, that axis. Well, also your eyelid pivots exactly around that axis. Now that's very important because if they didn't pivot around the same axis, you'd have interference between your eyelid and your eyeball. So remember, your axes for your U-joint have to go through the center of the sphere or eyeball, and the eyelid needs to go through the center of the sphere or the eyeball with just an offset up under here to give a little clearance between the eyeball and the eyelid. Now, when we look at how we lined up the servo horn and the output into the eyelid, you notice that they're nearly parallel. Why is that? Let's talk about positioning the servo horn with respect to an output and what different effects those have on the animatronic system. Here we have our servo horn, and here we have our eyeball output. What we want to do is we want to be able to close this eyelid as fast as possible. In order to close it as fast as possible, we want as much motion in the X direction as possible to equal the same or more amount of X direction motion as possible. So to do that, you put it at 90 degrees to the output. Because for small angles, let's say plus or minus 45, the majority of your translation is in the X direction. You have a very little bit in the Y, but most of your motion goes in the X, which means most of your motion goes in the X direction over here. So you can connect it with a wire, those two, and now you get the motion you want. You get the most motion to close the eyelid. So you want it to close quickly, so this is how you get the most motion out. Let's look at the alternate option here. If we have the servo horn pointing 90 degrees to the output of the eyelid, if we go connect this with a wire between here, a rigid member between there and there, then when this horn turns plus or minus 45, this being where it is now at 0 degrees, then you can see that a majority of your motion is in the Y direction and very little is in your X direction if we have it rotate from here to here. So with very little motion in the X direction, you get very little motion in the X direction of your output. So in order to get this eyelid to open and close, this horn would have to turn almost 180 degrees to get it to go one direction. Horns only move so fast, so if you need them to move quickly, you should have it set up more like this. In order to get this to close completely, this would have to turn 180 degrees back and forth, which takes a long time, which makes the motion very slow. Let's talk about toggle positions. Toggles can happen on the input and on the output. However, having a toggle position on the output is usually a very bad idea, and let me explain why. If this horn rotates clockwise, it pushes the rod this way. This output here is in a toggle position, meaning this output rod and this output arm are directly in line. If we apply a force to the right, this arm could go this way, or it could go this way. You don't really know. It's right on the edge. Plus, the force is going right through this pin, so it's really inefficient. So you're pretty much going to jam up your eyelid, which sounds weird. So you want to make sure you keep this arm at least 45 degrees to your push rod. Now, the same thing can happen on the other side. You could have this also, too, is a toggle position. You can imagine if this servo tries to go this way, it's going to pull on this arm, and the arm could go this way or it could pop this way. And also, your force is directly through your input pins, so it's pretty much jammed up. If your servo tries to go the clockwise direction, then it can't go any farther. This output can't go any farther, and it's going to jam up. These are both examples of toggle positions, and you want to stay away from these when designing animatronics if you're going to use a push rod system. The closer this angle gets to this angle, meaning into a straight line, either overlapping or in a straight line, that's a toggle position, and you're going to jam up. You want to stay away from that in your animatronics design. So you may be asking, how do we move this eyeball? This is a Igor animatronic that I made. It has eyeballs that can move in both directions. And if you look here, you have two little hooks. So I designed in little posts. They're kind of hard to see, but you can see that post. Now let's look at the actual animatronics design. So now let's look at the animatronics test rig, and you can see some of the rules that we followed earlier. Notice the output arm from the horn from the servo is 90 degrees to the linkage. This is about as efficient as it can get. Note too that your eyeball, which has your U-joint here, that pin that it rotates around in this direction is 90 degrees to this connector. So it also is extremely efficient. So now you can see the post on the side of the eyeball there. So because of that, when this horn moves, you can see the eye rocks back and forth. And note that to go left and right, the horn never goes more than plus or minus 45 degrees to this connector, so the connector never goes directly in line. They never get in line. If they were in a straight line, this eyeball would jam up. So that's how that works. Following the same rule, you can kind of see it here. You have a horn under here with a 90-degree connector to that horn, which connects to this eyeball here at 90 degrees, so it rotates this direction. We'll open the eyelid. And if I go under here and manually turn this horn, you can see that it rotates the eyeball up and down. So they follow the exact same rules on both servos, and the eyelid follows the same rule of staying away from toggle positions. Combined all those three together, and you've got yourself an animatronic eyeball. Well, so now we've figured out how the eyeball mechanism works. We've also talked about how the servo to output linkage works and how you want to keep the angle plus or minus 45 degrees typically to keep things efficient and moving smoothly and about the equal speed at all times. How do we assemble this so that all the parts are in their known position? You could easily just glue it down and hope that things line up correctly, but when you're talking about tight tolerances, that could be tricky, especially if you got something that's got a very small surface and you got to get it perpendicular to the surface you're trying to glue it to. So I'm going to give you a tip here that I use, that I've used in my daytime job, and hopefully it'll give you some ideas on how to attach parts together and align them properly. This works great for if you have a small printer like I do and you have to split parts up and then attach them together and make sure everything lines up, or if you're just making individual parts to reduce the amount of support material and you want to make sure things line up correctly. It works very well for both these cases. So let's discuss how we're going to attach these together. Here I put together a pretty basic example. What if we want to attach these two pieces together? Well, we use the term called plane line point. And what does that mean? That means that these two pieces have 3 degrees of freedom, meaning it can move this way, it can move up and down, it can move in and out, you can rotate this way, and this way. So you've got 3 translations and 3 rotations. So we need if we can get rid of all of those, we know that the 2 parts are lined up. So the way that we do that is we already have a plane. You want to have a plane, a line, and a point. Okay? So when you attach these together, you got 2 planes coming together. So you got a plane, right? But because of that, you can move this direction, you can move this direction, you can go like this, right? So you've got 2 translations left and a rotation. Now let's say we pick a common point. Let's say these 2 circles here. So you have plane and a point. Well, I can still rotate around that point. What keeps that from rotating? Well, a line. If we draw a line between 2 points, it's completely constrained. The plane takes out motion so this direction. The point takes out translation up and down and forward and backwards, but you can still rotate. And the line keeps you from rotating. So what does that mean, and how do we take care of that? Well, typically when you attach 2 pieces together like this, you want to pin them together. Pinning a tight tolerance pin is a very good way of locating things. So why not use tools that you already have? In my case, 2.85. You have filament, which for short distances is pretty darn straight. And you can go in here and straighten her out if you want to. Okay, when we look at this filament specifically, it is 2.8 millimeters. So what we're going to do is I went and put in holes and slots. So why is this a slot? Well, when these go together, these points will always line up here, right? Because you can align these. However, if you have 2 holes over here and either one of the holes is not positioned correctly, it will not go together. So a proper way to align things is one of these has to be a slot, right? So I put pins in each one of these holes. One pin will always fit. The other pin needs to be a slot for the tolerance, okay? So what we'll do is we're going to grab ourselves a drill bit that is 2.8 millimeters and drill these holes out to the proper size. So let's do that. I'll be right back. Okay, so I drilled these holes out to 2.82 millimeters. So if I did this right, this filament should fit tightly in there. And what we do is, you don't want it too long. Just go in here with your flush cutters. Okay, there's one. And let's put the other one in. Okay. So you'll note for short distances, those are pretty straight. So let's go through here. So your plane is here. Here's your point. This one goes into this one. Now notice this can still rotate, but now this slot here keeps it from rotating. So if we go like that, there you go. And that is perfectly aligned. So now if you wanted to attach this, you could go in, put your adhesive in here, and clamp that together, and both your parts are aligned perfectly. Also, it adds a little bit of strength to it, but that's how you align 2 pieces, especially so if you've got something that needs to be oriented in the exact direction, consider putting in two holes in one part and a hole in a slot in the other, and you can use your filament, whether it's 1.75 or 2.85, to align your part. So that's how you attach printed parts together accurately and guarantee that they're in the right spot. It may not seem like a big deal for if you're just attaching 2 parts together, but you could imagine in animatronics, if you have a base plate and then you have an eye mount, and off the eye mount is a jaw mount, and off the jaw mount is a clip that holds a sensor. You've got 4 or 5 parts stacked on top of each other, and each one of them has tolerance of how you put it together. So the more error you can take out of your assembly, the more accurate it's going to be in the end. So you don't have to use it, but I can guarantee you if you use 2 holes for 2 pins and one side of the part has a pin and a slot, you will have very accurate aligned parts when you make animatronics. Why is this important? Well, for example, remember back on the U-joint here. We want to make sure that this U-joint is positioned exactly where we want it with respect to the eyelid. If it's too close to the eyelid, you won't have any clearance between your eyelid and your eyeball. So you'll have interference, you'll glue it together, and it won't move. So what do? In this case, put a hole in there that is suspiciously the size of your filament. Right. There we go. That. And if you design your universal joint with a pin, you can pop those two together and locate it. All right. So in this case, this takes out all the translation. There's still this rotation this way, but if I attach this correctly, I can attach the eyeball separately and get that rotation correct and everything will be lined up. What we don't want is this U-joint to be too high up or too close to the eyelid where the two interfere. So using a pin and a slot is an excellent way for locating parts when doing animatronics. I can't stress that enough. Design it in to all of your assemblies where you have to glue parts together. Hopefully you learned a little bit about how the eyeball mechanism works, how you get a universal joint to work, how you can make your own, how you go about aligning servos so that you get the right motion and you stay away from toggle positions where your servo can jam up your system. And finally, the biggest thing I hope you take away is by designing your assemblies so that they have alignment features, specifically pins and slots, you can take out of a lot of misalignment that begins to build upon itself when you're building much larger assemblies. It may not seem like a lot when you have 2 parts attached together, but when you start attaching parts attached to parts attached to parts, those errors build up and things don't line up anymore because you think they're lined up, but every degree that you're off in each part adds up down the road. So I think that's good for here. We're going to leave it there. Not sure when the next episode will be because of the closing of the house. However, the next episode, I hope, we'll go through a basic Arduino code example and give you the basics of how to capture data and play the data back on a servo on repeat, which is the heart of the animatronic project itself. So until then, hope you're enjoying this. If you have any questions, comment below. I'll try to answer them, or contact me on Twitter. I'll put my contact information in the bottom. Be glad to hear from you, and if you have any questions, maybe I'll include it in the next video and try to get those questions answered, because that's the point of these videos anyway. I hope people are learning a lot, and hope it's been a lot of fun. So we'll continue on next time.